points coincide. Similarly, the freezing point and melting point also coincide. That means if you are boiling, if you are keeping the pressure constant and if you are boiling a liquid, then the temperature at which you find the first droplet of is some temperature T, and now you come in the reverse direction. That means you have a vapor and you are cooling it isobarically at the same pressure, and the temperature at which you find for the first droplet of liquid, that is what is known as dew point temperature, and the temperature at which you find the first vapor bubble is known as the boiling point. And for the pure fluids, the boiling point and dew points coincide. Similarly, the freezing point and melting points coincide. For example, at 1 atmospheric pressure, the boiling point of water is 100 degrees centigrade. Similarly, the dew point of water is also 100 degrees centigrade. Why I am stressing this is for mixers, that means a mixture of two refrigerants, the boiling point and dew point may not coincide. Similarly, the freezing point and melting point may not coincide. Okay. Now this is the repetition of whatever I have stated earlier. The critical point, the definition of critical point, it's the point at which the saturated liquid and saturated vapor lines merge, and the triple point is the point at which the solid, liquid and vapor phases coexist in equilibrium. Let me give some typical values of critical point and triple point for water. For example, for water, the triple point is 0.1 degree centigrade, and the pressure at triple point is 0.006112 bar, and its critical point is at 374.2 degree centigrade, and the pressure at critical point is 221.2 bar. And for carbon dioxide or for dry ice, the triple point is minus 56.6 degree centigrade, and the pressure at triple point is 5.18 bar, and the critical point is 31 degree centigrade and 73.8 bar. As I mentioned earlier, all these things are very important, and they play a major role while selecting suitable refrigerants for a given application. So we will be discussing the importance of triple point, critical point, etc. when we discuss selection of refrigerants. Now in most of the refrigeration applications, we really won't be dealing with the solid phase. That means we won't be dealing with solid and liquid phases or solid and gaseous phases. Of course, there are some applications. For example, if you are using ice for a refrigeration purpose, then obviously you will be dealing with solid liquid equilibria. Similarly, if you are using, let us say, dry ice, then you will be dealing with solid gas equilibria. But in most of the thermodynamic cycles which we are mostly interested in, we will be dealing with liquid gas interface. So we will be concentrating most of the time on phase diagrams for liquid gas phases. So let us look at TS and PS diagrams for liquid vapor regimes. There, as I said, they are very useful in refrigeration calculations. So let me show a typical TS diagram. So here we have entropy S on the x-axis and temperature T on the y-axis, and this is a typical curve, and this is your saturated liquid curve, and this is your saturated vapor curve, and this is the point at which both of them join, that is known as your critical point. And on this diagram you have this subcooled liquid region, and this is superheated gas region, and this is liquid plus gas two phase region. That means you have a single phase region here, two phase region here, and again a single phase region here. And on this figure I have shown two isobars, that means two constant pressure lines, P1 and P2. So you can see the shape of the constant pressure lines. It has slopes in the single phase regions, whereas it becomes horizontal in the two phase region. This is again in accordance with your Gibbs phase rule, or based on the fact that when a liquid boils at a constant temperature, pressure also remains constant. That's the reason why you have a horizontal isobaric line in two phase region. And here the pressure P1 is greater than P2, that means pressure increases in this direction. And let us look at one isobar 1, 2, 3, 4, and here the region 1 to 2, that means this region is in the subcooled condition, and this region is in the two phase zone, and this region is in the single phase superheated condition. One thing I would like to point out here is that normally the data for the subcooled liquid region is generally not available. We have the data for this region and data for this region. So most of the times we do not have the data for subcooled regions, and subcooled data is also required for refrigeration calculations. In such cases we make certain assumptions and certain idealizations. Here, as I mentioned, this line is a constant pressure line and this line is a saturated liquid line. Even though they seem to be distinct here, in actual case they are very close to each other. So one approximation we can make is they almost merge. That means the isobaric line coincides with the saturated liquid line. So that is one of the assumptions. It's a very useful assumption. And another assumption is that, and it can be shown using your thermodynamic relations, that if you want, let us say, the properties at this point A, which is in subcooled region, so they can be approximated with saturated liquid properties at point A dash. Okay, this is one very useful assumption, and most of the time we will be using this assumption. That means if you want, let us say, a liquid exists in subcooled condition, and let us say that its temperature is 30 degrees centigrade and it is at some pressure and it is at subcooled condition. So we would like to find out what is the internal energy and enthalpy at these conditions. So what we can do is, instead of finding the subcooled conditions, we can assume them to be equal to the saturated liquid properties at 30 degrees centigrade. So this is one very useful idealization, and we will discuss this when we do or perform refrigeration calculations. Now, similar to TS diagram, we can also have PS diagram. This figure shows the PS diagram here, and these are the isobaric lines. Since you have pressure on the y-axis, obviously isobaric lines become horizontal and pressure increases in this direction, and on x-axis you have enthalpy. And I have not shown here, but the isothermal line, that means constant temperature lines, will be typically something like this. Okay, that means again they will be horizontal in the two-phase region, and they become sloped in the single phase superheated region, and they become almost vertical in the low pressure zone. And here again I have shown the process for the pressure P1, the process 1, 2, 3, 4, where 1, 2 is in the subcooled liquid region, process 2, 3 is in the two phase region, and process 3, 4 in the superheated region. And again you can see that as I have mentioned, the properties at this point A can be approximated, and they can be taken as equal to the saturated liquid properties at this condition. Okay, and this pH diagram and TS diagrams are very useful for performing refrigeration calculations, and we shall see most of the times we will be showing the cycle diagrams on the TS and PS diagrams. So one use of these TS and PS diagrams is that you can find out the required properties using these charts or diagrams. And second use of these charts is you can also represent the thermodynamic cycles on these charts, so that you can directly perform various calculations using these charts. Okay. So as I mentioned, and from your from the last class, using the second law of thermodynamics and from TDS relations, it can be shown that for a reversible process 1, 2, let us say that a process, a reversible process 1, 2, the area under the curve 1, 2 in TS diagram is equal to the heat transfer during the process. This is from your Clausius inequality, where entropy change in a reversible process is given by the heat transfer rate in the during that process divided by the temperature at the boundary. So using that statement, we can easily show that the area under any curve 1, 2 on TS coordinates or on TS diagram is nothing but the heat transfer during the process. So if you can plot the process on the TS diagram, and if you can measure what is the area under the curve 1, 2, then you have the heat transfer during the process. This is very useful. And for all practical purposes, as I mentioned just now, the enthalpy of sweat may be taken as equal to the enthalpy of saturated liquid at the subcooled temperature. Now let us look at saturation properties of pure fluids. What do we mean by saturation properties? Let us say that Again, I would like to repeat here that most of the times we will be dealing with liquid gas either in the single phase or two phase or in superheated regions. So, how do we evaluate the properties of liquid gas mixers in two phase regions? So, the equations shown here are for finding out the two phase properties, that means liquid gas equilibrium properties. For example, this equation gives the specific volume of a two phase mixer in terms of saturated liquid specific volume, saturated liquid specific volume and saturated vapor specific volume, and X here is nothing but your dryness fraction or quality. I am sure that you have used these correlations, or you have used these relations while performing calculations in basic thermodynamics. Similarly, you can express the specific internal energy U of a two phase mixer in terms of the dryness fraction X and the saturated liquid internal energy and saturated saturated vapor internal energy. Similarly, the properties of enthalpy and entropy of the two phase mixer can be expressed in terms of saturated property and the quality. That means if you want to find out the mixer properties, you need to know what are the saturated properties first, and you also need to know what is the dryness fraction or quality. And you probably remember that the quality or dryness fraction is defined as the mass of the vapor in the mixer divided by the total mass of the mixer. So, that is the definition of dryness fraction. Now, let us look at the second method for evaluating thermodynamic properties. We have seen thermodynamic equations of state and some thermodynamic diagrams or thermodynamic property charts. So, now let us look at thermodynamic property tables. Normally, the property tables are available for saturated region, that means for the two phase region and also for the superheated region. And the saturated and superheated property tables for steam are used for calculating power plant calculations, and I am sure that you must have used them in your basic thermodynamics. And the internal energy, enthalpy and entropy values reported are based on a reference state which may vary from table to table. This is a very important point. That means when you are using a thermodynamic property table, as I mentioned earlier, you do not have any absolute values for internal energy or enthalpy or for that matter entropy, provided you are not using the third law of thermodynamics. So, normally the internal energy, enthalpy and entropy values are values with reference to a particular datum state. That means all tables, they first define a reference state, and at that reference state they give arbitrary values for internal energy, enthalpy and entropy, and the internal energy, enthalpy and entropy at any other state are given with reference to the reference state. So, basically what the value of enthalpy, for example, the enthalpy of H that you see in a table is nothing but H minus H corresponding to the reference state. Okay. Similarly for the internal energy and entropy. So, as long as you are using the same table, then it does not make any difference, and what reference values are chosen do not come into picture, because normally we will be dealing with enthalpy changes, entropy changes, internal entropy changes, internal energy changes, etc. So, the reference state does not come into picture. So, you are safe as long as you are using the same thermodynamic property table. But if you are using tables from different sources, then you have to know what are the reference states. You must make sure that the reference states are not different. If they are different, then you have to make suitable corrections and then only use the enthalpy and entropy properties. Normally the saturation property tables are either temperature or pressure based. For example, a saturated temperature based property table, they give temperature as an independent variable, and they give all other properties as functions of temperature. That means you have for example, let us say take water. They say the typical table for water looks like this. Let us say the temperature of water is at 10 degrees centigrade. Then the table gives you, the saturated table gives you what is the saturation pressure at 10 degrees centigrade. Then it also gives you what is the saturated liquid properties at 10 degree centigrade and what is the saturated vapor properties at 10 degree centigrade. So, this is a typical table based on temperatures. Similarly, you can have saturation table based on pressure. That means the pressure is the independent variable. Let us say that 1 bar pressure, then at 1 bar pressure they give what is the saturation temperature and what are the saturated liquid and vapor properties. So, you can have either saturated either temperature based saturation tables or pressure based saturation tables. And normally the superheated tables are available for different pressures and degrees of superheat. We shall discuss these tables when we actually perform the refrigerant calculations. And if you look at any of the textbooks on thermodynamics or refrigeration, at the end of the textbooks all these property tables are available for a wide variety of refrigerants. And I am sure that you must have used these tables in your basic thermodynamics. Okay. Now let us look at some common thermodynamic processes. In refrigeration and air conditioning, we come across a wide variety of processes, and if you want to find out what is the performance of a particular process or a performance of a particular cycle, we need to know or we need to understand that particular process, and we have to estimate what is the heat transfer during that particular process, or what is the mass transfer during that particular process, what is the entropy transfer during that particular process. All these terms are required in order to evaluate the performance. So, in the let us look at some of the very basic processes. I will give the basic process and a typical example and the suitable equations for work transfer, heat transfer, energy transfer or energy change, etc. Okay. So, the first process, a simple process, is a constant volume or isochoric process. So, isochoric process means the volume does not change, and a typical example is the heating and cooling of a gas stored in a rigid vessel. So, that means we have a rigid vessel and it consists of a gas, and which is the system here, and we are heating the gas. And this process, this example is typically a non-flow process. That means neither the gas is leaving nor entering into the rigid vessel. For this kind of a system, if you are heating or cooling the gas, what are the typical equations for work transfer, heat transfer and entropy change? So, those equations are given here. How did we get these equations? For example, this equation, how did we get this? For a non-flow process, if you remember, the work transfer 1W2 is given by integral PdV integrated between 1 to 2, and here dV is the volume change. Since it is a rigid vessel, dV is equal to 0. So, work transfer rate is equal to 0. So, that is how you get this equation. So, the work transferred in a simple heating and cooling of a gas stored in rigid vessel is 0, provided we do not have any other modes of work transfer. For example, you do not have any electrical heater or any other magnetic or chemical modes of work transfer. Okay. Then we can find out this expression for heat transfer rate during this process using the first law of thermodynamic process, first law of thermodynamics for a non-flow process. As you know, first law of thermodynamics for a non-flow process is given by 1Q2 is nothing but 1W2 plus integral du. Since 1W2 is 0, you simply have here 1Q2 is equal to integral du. Since this is the property, the integral du can be written as U2 minus U1, where U2 is the total internal energy at state 2 and U1 is the total internal energy at state 1. Of course, this is based on the assumption that other changes like kinetic and potential energy changes are negligible. And this equation can also be written in terms of the first TDS equation. If you remember, the first TDS equation is given by TDS is du plus PdV, okay, and PdV is 0 because there is no volume change. So, TDS is simply equal to du. So, ds is du by t. So, if you are integrating this between state 1 and 2, you get that S2 minus S1 is nothing but mCV into ln T2 by T1. Okay. You can also think of other non-flow processes. For example, another very simple example of a constant volume process is that of a heating or cooling of a solid. For example, when you are heating or cooling a solid over a temperature difference which is not too large, then its volume remains constant, and the heat transfer rate during that process is simply equal to mc into delta T, and for a solid